So in this topic, we're going to study the theory and algorithms of CPU scheduling. And you'll also have practice with system calls that are related to CPU scheduling with Linux, as well as we're going to study realistic CPU scheduling with operating systems such as Linux, the actual scheduler of Linux. Then finally, we end up with simulating CPU scheduling algorithms. So we'll teach you how to write simulation programs for scheduling algorithms, okay? And maybe after we show you one or two simulations, that might give you the inspiration of having your project to be simulation of a particular CPU scheduling algorithm, okay? But it has to be realistic plus lots of other constraints as well. So the material is balanced, okay? Today, hopefully, we can cover the following, which is basically just simple motivation to CPU scheduling. And we have been talking about it, actually, in the last few classes. And then we look at two different sets of CPU scheduling algorithms, basically the preemptive and non-preemptive CPU scheduling. Then we'll see what kind of performance measurements that we are interested in to compare one CPU scheduling to another, and how we can collect these performance measurements. And then we show you the different types of CPU scheduling algorithms and their tracing. How can you trace them, okay? So the scheduler, as you know here, the kind of scheduler we're talking about is CPU scheduling. And it is responsible for picking up a process to be executed by the CPU, right? That's the aim of the CPU scheduling adopted by an operating system. And this has to be simple because it's called very frequent. So we want the simplest complexity for this kind of algorithm. I've started talking a little bit about Linux because we have to relate things to one operating system, and then we move to general, and then go back to Linux for more specific details of these scheduling policies. So we call the policy, okay, is how, okay, we select a particular process that is ready to execute, how we select it to be executed, okay? And we have various types of policies. In fact, Linux, it has the RR policy, and it has the FIFO policy, and the default policy that is called others, schedule others, okay? The schedule others actually is an RR, okay, which is round robin policy. However, these two, they will work a little bit different than the basic FIFO and RR, okay? So at the very beginning, you need to know what is the basic FIFO, basic RR, and then once we cover all that kind of material, we will go into the details of FIFO and R of Linux, how they really work, okay? They have a little bit of variation. In fact, the main difference is that FIFO and RR, they implicitly also have priority scheduling. Priority scheduling, which means the highest, the priority of the process, okay, means the highest probability that it will be executed, okay? So we are favoring highest priority processes on lower priority processes. And in fact, in Linux, we have like these processes from 1 to 99 being the real-time or system processes. These are the priorities for them, 1 to 99. These priority for real-time or system processes. And always, the priority of other processes, which are user processes, is 0. Okay? So this is we call the static priority of processes. However, later on that, you will know that there is another, okay, group of priorities. It's not static priority. We're going to call it the nice priority. So since the normal processes, which are user processes, always have priority 0, means they are the lowest in the system. Okay, lowest in the system means any real-time process or system process will execute first, and only then what? Users processes. You can see here that the priorities that we're looking at, we're saying that the highest the integer is the highest the priority. Okay? In some systems, with the lowest, the integer is the highest the priority. So preemptive policies, non-preemptive policies, preemptive algorithms and non-preemptive algorithms. For preemptive scheduling, a process that is under execution in the CPU can be interrupted by another process. Can be interrupted by another process, even though it has already been chosen and it has been what? Executing for a while. This is preemptive. I can preempt the process out. Okay? The process can preempt another process out based on the policy that has been adopted by the system. In non-preemptive, if the process has been chosen to execute, then it cannot be preempted, okay? Because it already has been chosen to execute. This is the difference between what? Preemptive and non-preemptive scheduling. We will see that we have actually variations of the same policy being preemptive and non-preemptive. Of course, here under non-preemptive, processes will not execute for infinity until they finish. Most of the time, you know, a process will invoke an I/O, okay? Or maybe it can pause, right? And for these reasons and many other reasons, the process will be what? Will be moved out, okay? And then another process will be picked up for execution. But it cannot be interrupted by the policy itself to execute another process because it is non-preemptive. With preemption policies, where we can interrupt a process under execution, we have to take some precautions. Some precautions. If a process is executing and out of a sudden it had been interrupted, okay, so it has to be moved out, right? And another process has to take over, right? So this process that is interrupted might be executing some kind of critical section, okay, portion of the code, okay? In this critical section, why I call it critical section? Because I call it a critical section because the process is doing some kind of modification to a data, okay? To a data. And that data might be shared with other processes. So halfway through the modification of the data, the process is interrupted, okay? And what would that result? You are updating, the process is updating the data, but not finished, halfway through. So the data will be left inconsistent. It's not the previous one, neither the new one, and so on, right? So when another process accessing this data will find the old data because it's not finished. However, this process assumed what? It has been changed because it's in the process of changing it. And the sequence of changing the value of a data involves more than one instruction. Multiple instructions. Even if you have like a data, say count, and you want to execute count plus plus. Count plus plus is not one instruction. It's 3 instructions, right? Load the value that is in count, right? Increment it by 1, and then restore it back. 3. So if the interrupt happens in between, then everything is wrong, right? Especially if there is another process that will be working on this data. So that's something we have to take care of by using some kind of coordination. Or maybe we can look interrupts, okay? We can disable interrupts before the code that does that kind of change to the data, okay? And enable it after that. Enable it after that. Only for these sections that are very critical. We call them critical sections. But if these sections are long, involve many instructions to execute, then it's very much like we're given this process longer time to be executed in the CPU. And this is against our main goal, which is a multitasking system. So we should not do that in this case, okay? So other solutions has to be taken care of, has to be adopted. Another problem might be that the data being currently updated, okay, is a data that corresponds to the kernel. Okay, is a kernel data. So this process might be a system process, interrupt to another system process, and so on. But it's doing some kind of modification to kernel data. And if this kernel data is left in an inconsistent view of it, then what? The whole kernel might corrupt. Okay? So the problem even is what? Is bigger, right? So for these are, I mean, the main things that we have to take care of when we talk about what? Preemptive scheduling. Other problems later on that we will talk about, which is the fairness, okay? Fairness. Is it like fair to keep interrupting a process? Never finish the slice that had been given to it to execute? And what are the solutions for that? So when a process is interrupting, we said we do the housekeeping thing. We called it the housekeeping. And that kind of interruption will result in context switch. So the CPU will switch from the context of a particular process to a newer process in order to execute it. Context is switching. And that's an overhead, right? A delay in which nothing useful is done by the CPU. The dispatcher, okay, the dispatcher model in your system, it does these things. It does the context switching, which we're familiar with now, and the switching to the user mode, okay, so that we can interact with the programs, okay, as well as what? Jumping to proper location in the new user program to be executed, okay? These three things that are done by the dispatcher model, they need time. And that time, again, is what? An overhead. It's a waste. CPU is not doing something useful during this time. So that's why we call it the dispatch latency. Dispatch latency. So dispatch latency is the time that's needed by what? The dispatcher to perform the work of it, which involves these three things. Now the CPU scheduling algorithms, or the different policies that are available for us to schedule processes, okay? This is the basic set of these CPU scheduling algorithms. However, we have other specific sets to specific type of systems, such as real systems. We have category of scheduling algorithms for it, okay? These basic scheduling algorithms include the FIFO, or sometimes we call it first come, first serve, and the shortest job first, as well as the preemptive shortest job first. So, as I mentioned before, you might have the same policy, but non-preemptive and preemptive. The default is being non-preemptive, okay? So the preemptive shortest job first, we call it what? Shortest remaining time first. Shortest remaining time first. And you will see why when we trace these algorithms. We also have priority, that is preemptive, non-preemptive. We also have round robin. So these are the most basic ones, okay? And then we will introduce CPU scheduling policies that are meant to work with multiple queues, multiple waiting queues instead of one queue. As well as we will introduce also later on multiple processors, okay? Multiple processors, and scheduling processes that work with them. One of them is the Linux scheduling algorithm. So now, since we have multiple algorithms, you need to pick up one of them that suits your system the most. So how would I know which one suits me the most? Well, first of all, you need the best, right? So the question, I need to choose the best. But how do you define best? Okay? So if I want to define best, then I have to be interested in certain measurements. Huh? So I need to have some kind of performance measurements of interest, okay? And the collective of values that I will get from these form what is called the best, okay? The goodness of the algorithm compared to another algorithm. The one that will give me the highest, I will choose it for my system. So the things that we are really interested in, okay, finding out the waiting time, how long it will take a process to be executed, which means how long the process will be waiting in the ready queue before it gets the CPU, okay? But you know, the process might wait multiple times, okay, because it might need to take turns with the CPU. So we'll take different slice, which means when I say waiting time, I'm talking the total of all waiting times for a particular process. That will form what? The waiting time for the process. And also I might be interested in the turnaround time. The turnaround time is the time needed for a process to finish from the time it had been in the ready state of it until it's finished. That will include the waiting time plus the time that is spent in the CPU. Right? From the time it arrived at the queue, the ready queue, it will take one chunk of time executing, then to go back to the ready queue, then again later on will take a slice of time to execute, and then queue again in the queue, right? So the summation of all waiting times in the queue plus the times that the process has taken with the CPU executing, all of that forms what? The turnaround time, the time needed by the process to finish. As well as sometimes I am interested in the CPU utilization. Okay? The CPU is an important resource, and I really need to utilize it as much as I can. Okay? So the process the policy that gives me the highest of that will be also something good for me. There are other performance measurements of interest that we'll talk about them in a while. But the collective of these, okay, might give me an indication of how to measure the goodness of the algorithm. So we say CPU utilization, which is the percentage of the CPU being busy. Okay? Throughput, the number of processes that had been completed in a unit of time. That might be a second or a minute. It depends what's your unit of time. Okay? This is productivity, right? Throughput. The turnaround time is the completion time, from the time the process arrived to the ready queue until it's finished. So queuing plus service time. Okay? The waiting time is the queuing time, which can be multiple chunks of waiting time. And the response time is the very first chunk of waiting time. It's the very first chunk of waiting time. A process might be waiting multiple times, right? The very first chunk of waiting time is the response time. How long it took the CPU to respond to the process. But responding to the process doesn't mean that this is your only queuing. You might queue again. Your first response. Your first response is called what? The response time. The process's first response is called the response time. So how do we look at these performance measurements? Our aim is to maximize CPU utilization. Maximize throughput. Productivity, okay? More number of processes finished within a unit of time. And minimize the rest, such as turnaround time, waiting time, and response time. Okay? Turnaround time and waiting time, they are what? Very related, okay? Because one important part of turnaround time is the waiting time. So if you have the waiting time, and you know how long the process has been executing, you can easily calculate turnaround time. It is the waiting time plus how long it spends in the CPU. Now we look at these algorithms, okay? So here the aim is to understand how the algorithm works, and if you are given a number of processes, can you trace the execution using a particular policy? Okay, so that's what you need to practice on. The first come, first serve is as easy as this. Whoever comes first will be served first. And it doesn't need to queue again. I'm talking about the basic FIFO policy. Don't have to queue again. Once you give in the CPU, stay there until you finish. Okay? And then another one will take over. So there is only one waiting time. One chunk of waiting time. Which means in this case, the response time equals to the waiting time. Since the response time is the very first chunk of what? Waiting time. And if the process is waiting only one time, it's the same. Okay? However, later on you will see actually, in reality with operating systems, FIFO doesn't mean that the process will wait only for one time. Okay? Multitasking says, okay, I will give you the execution time you need as long as you did not pause, you did not ask for I/O, right? Because I have to take others as well. This is a time that I'm not doing anything as a processor, right? So the CPU is not doing anything useful during this time. So basically, it has to take another process. And what will happen to this process? Has to wait. Okay, has to wait. But wait where? At the rear of the queue or front? Okay, all of these, okay, different questions that we will talk and answer. We'll answer it when we talk about a particular, okay, scheduling policy with a particular operating system. But for the basic one, as we mentioned, once get service finished. Now, the shortest job first, it says that, well, let's be a little bit realistic. A process that needs 5 milliseconds, okay, doesn't really need to wait for 2 processes that came before, and each one of them needs maybe 100 milliseconds each. Right? It's not really of a big harm, okay, for this process to be executed first. Instead of waiting 200 milliseconds for 2 processes where each needs 100 milliseconds, okay, it can be executed first. And what will that affect? What will be the effect on the other 2 processes? A delay of 5 milliseconds only, right? So it's something natural. And actually, you've been doing in the shopping malls, right? If you are queuing there at the cashier and you find someone only holding 1, 2 items, you naturally will ask that person to what? To jump queue in front of you, okay? I'll be thankful for that, right? So, and you will not be affected. And you will feel bad if you're holding 2 items while in front of you 2 trolleys full of things. Each one will take maybe 5 minutes, while you might take 20 seconds to finish, okay? So this is natural, and it has a very high impact on the performance of the system. We distinguish between 2 types of shortest job first, preemptive and non-preemptive. Okay? The preemptive one, the non-preemptive one is what I explained. Okay? But the preemptive one, if a process under execution, okay, is left with 5 milliseconds, already under execution, but left with 5 milliseconds, and assume that at that point of time, another process arrived at the queue, which has many processes. Another process arrived at the queue that needs only 2 milliseconds, while the one executing is left with 5 milliseconds. So under preemptive scheduling, this new process can take over, and the currently executing process can get interrupted, right? So here I'm comparing what? I'm comparing not the times needed by the processes. I'm comparing the time needed by the new arrival to what? To the time that is left for the process under execution, which is the remaining time for the process under execution. That's why we call this scheduling policy shortest remaining time first. Shortest remaining time first, okay? Now these shortest job first and shortest remaining time first, each one of them corresponding to different categories, preemptive and non-preemptive categories. And these are the 2 categories that we have. In fact, each one of them is the optimal scheduling algorithm for its category. Optimal, which means you can't find better. Okay? If I can't find better, why do I need to study all the other scheduling algorithms? Isn't it? It has one problem. It cannot be implemented. Because to implement shortest job first and shortest remaining time first, look, the decision that we took is based on how long the process needs to execute. Right? How long the process needs to execute. And this kind of information, do you know it? Can we know it? How long the process will be executing? We can't. We can't. So this piece of information is missing. Then why are we studying it? So first we only wanted to adopt it, right? And forget about the others. Now we say, why we study it? Because for us, we say this is the optimal, all right? And we're having multiple scheduling algorithms being suggested by multiple researchers. If you want to see which one of them is nearer to the optimal, then you have to know the optimal, right? So it is used as what? Benchmarking. For benchmarking of what? The other algorithms. Benchmarking for the goodness of the other algorithms. Now let's see just a trace, a very simple trace for these 2 algorithms. So first come, first serve. Assume that you have the following processes. We have P1, P2, P3. The burst time for P1 is 24, P2 3, and P3 3. Units of time. Units of time. Usually these are milliseconds. Milliseconds. It had been found in most of the systems, okay, that the burst time, or CPU burst time, which is the time needed by the process to finish, okay, these are estimated, right? These are estimated, okay. It is between 10 to 100 milliseconds. 10 to 100 milliseconds. It also has been found that the context switching time is between 0.1 to 1 millisecond. 0.1 to 1 millisecond. Okay, 0.1 to 1 millisecond compared to 100 milliseconds. It means 0.01, okay, is the delay, right? Compared to the actual execution time, right? 0.01 is the delay compared to that. Right. So here, the way that we're going to execute these processes, first the assumption here, all of these processes, they arrived at time 0, right? And they are ordered based on their appearance in this table, for example. So the first one to execute is P1. Assuming that the time we started to execute is 0, okay, then P1 will take the time from 0 up to 24 executing. And then it's finished. So what's the waiting time for for P1, sorry? What's the waiting time? 0. The time it arrived at T0. The time it starts execution at T0. What's the response time? 0. Right? Again. Now for P2, it arrived at T0. However, it starts executing at what? 24. Because it has to wait for P1 to finish. Okay? Now finishing these two together, we're already in 27. Okay, time is 27. And at this point, I have P3 to be executing, and that will take 3 milliseconds. So at T equals to 30, we have executed these 3 processes. Okay. How long P2 waiting? Had been waiting 3 milliseconds. And P2 had been waiting for 27, right? 27 milliseconds. And P3 had been waiting for? So P2 had been waiting for 24 milliseconds. Okay. P3 had been waiting for 27 milliseconds. Okay. Now I have these waiting times, 0, 24, 27. Usually we are not interested in what each process had been waiting for. But we are interested in the average of the waiting time. In the average of waiting time. The same thing for response time, turnaround time, throughput, and so. Okay, we are interested in what? In the average value. So finding the average of these, we'll find that is 17. The average, which means a process will be waiting on average 17 milliseconds in this system. Right? Now, if we do shortest job first, then we will be serving P2 first. Because P2 needs what? 3. Followed by P3 and then P1. Okay? So 0 to 3, that's the time needed for P2, and then 3 to 6 needed by P3, and then from 6 to 30 by P1. Now, if we calculate the waiting time, P2 waited 0 times, and P3 been waiting for 3 milliseconds, while P1 had been waiting for 6 milliseconds. You sum that, you find that's 9. 9 divided by 3, the number of processes, you have 3. So the average waiting time is 3. On average, a process will be waiting for 3 milliseconds, while in FIFO, 17 milliseconds. So this is an excellent improvement, okay? So this is again another example of shortest job first. We have these processes, but now we have arrival time, okay? We can say this arrived at this time, another process arrived at another time, and so on. So assuming that the arrival time is given there, okay, so I have process P1 arriving at T equals to 0, and it needs 7 bars time, okay? P2, it arrived at t equals to 2, it needs 4, and so on. Okay? Shortest job first says that, okay, at a particular point, look at the queue, who's there, choose the shortest. Right? Now we start at T0. We looked at the queue, who's there? P1 only. P2 arrived later, right? So at t equals to 0 here, I have only in the queue who? P1. P2 is not there, did not arrive yet. So that's the shortest, because there is only one. Okay, so I'll be serving what? P1. P1 will be served until t equals to 7. Okay? Now when t equals to 7, I will look at the queue. Who's there? P2, P3, P4. Right? Because the time now is 7. Right? So now I'll pick up the shortest of them, which is P3. Because P3, it needs what? 1. The shortest in terms of parse time, right? So I'll be what? Serving P3. You know, if there are no new arrivals after that, you just serve them based on what? Here, and you don't have to keep worrying about the times here, because they are all arrived, right? So now P3 will be served 1 millisecond. After that, we'll be serving whom? P2 or P5? P2, because P2, it needs 4, but P4 also needs 4. But the one arrived first, so we're gonna serve that one, right? So if we have equal opportunities based on our policy, whoever arrived first will be served first, okay? The same thing for priority scheduling and so on. And then after that, we'll be serving what? A process P4 that needs another 4 milliseconds. So P2 took 4 milliseconds, and then P4 took another 4 milliseconds. Now calculate the waiting times. P1 arrived at T0, served at T0. So that's 0. Doesn't have to wait. Now P3 arrived at T equals to 2 and started the service at T equals to 7. So it means it had been waiting for 5 milliseconds, right? 5 milliseconds. 7 minus 2. Sorry. Now so we're talking about P3, sorry, P3. P3 arrived at T equals to 4, right? And started the service at T equals to 7. That is what? 3, okay, 3 milliseconds. And then after that, say here P2. P2 started the service at 8. However, it arrived at 2, so that is 6 milliseconds, okay? And then next here we have P4 started the service at 12, while actually P4 arrived at 5. 12 minus 5 is what? 7. So you sum that, you divide it by the number of processes, and you find that the average waiting time is what? 4. Okay? Now we'll give you another, yep. These? Okay. Now P1 arrived at, here started service at 0, right? And it arrived at 0, which means, was it waiting? No, so the waiting time is 0, okay? Now P3, it started the service at T equals to 7. However, it arrived at the queue at T equals to, P3 I'm talking, 4, right? Which means, yeah, the time between 4 and 7, the process was doing what? Waiting, right? So 7 minus 4, and so on, you continue for the rest of the processes. Now let's do the same, okay, for the same processes. We're gonna trace it for preemptive shortest job first. Preemptive shortest job first. To remind you, a process, a newly arrived process, can interrupt a process under execution if the time it needs is less than the time remains for the process under execution. Okay? Now we start by T equals to 0. Do we have any processes arriving at T equals to 0? Yes, P1. So P1 will get service and it needs 7. It needs 7. So we're expecting P1 to stay until 7. However, while P1 is in service, who arrived? P2 at t equals to 2. At t equals to 2. Now, P2, it needs 4. And P1 is left with how many milliseconds? It needed 7. It only got the service for 2 milliseconds, means it's left with 5. So the remaining times is 5 for P1. However, P2, it needs 4. So P2 will take over. P2 will take over. And what about P1? Will queue. Will queue with 5. With what? 5. Okay? Now, who's in the queue? Who's in the queue? P1 with 5. Okay? And I have P2 executing. Now, P2 executing from t equals to 2, I'm expecting it, well, it needs 4 milliseconds, so I'm expecting it to keep executing until 6. Right? But before 6, at t equals to 4, I have a new arrival. Okay? So at t equals to 4, P2 has finished 2 milliseconds, and it's left with 2 milliseconds. And at that time, a process which is P3 arrived, and it needs 1 millisecond. So who will take over? P3. So P3 will be executing now at t equals to 4. Now who's in the queue? B1 that needs 5, and P2 that needs 2. So now we have P3 executing from 4 to 5, okay? And at the time it is leaving, that's okay, important. At the time it's leaving, I have an arrival, which is P4. P4 needs 4 milliseconds. It needs 4 milliseconds. Okay, P4 new arrival, it needs 4 milliseconds. The time is 5. Okay? Who's in the queue? P2 needs 2 milliseconds, and P1 needs 5. So P4 will queue in between. And who will take over? P2. So now P2 will execute from 5 to 7. Okay? And since no more arrivals, I will execute P4 from 7 to 11. And then from 11 to 16, we'll execute what? P1. Okay? Now, for you are to calculate the waiting times. Waiting times. P1, what's the waiting time? Look, P1, it gets back, right? It took its first chunk here at the time it arrived. The time it arrived at t equals to 0 started the service. T equals to 0, correct? However, it did not finish. It has to queue and then come back again to service when t equals to 11. So from the time equals to 2 up to the time equals to 11, P1 was where? In the queue, right? So I can say 11 minus 2, 9. That's the waiting time of P1. Right? Now, what about the waiting time, the response time of P1? What about the response time P1? The very first waiting time. The time it arrived at the queue t equals to 0. Immediately good service. So the response time is what? 0. However, the waiting time is 9. Now let's look at P2. P2 arrived at t equals to 2. And it started the service at t equals to 2. But did it finish? No. It started again at t equals to 5. And then after that it's finished, right? Which means from t equals to 4 up to t equals to 5, which is 1 millisecond, where was P2? Queuing, right? So that's 1 millisecond for P2. Okay? Now, if we look at P3, arrived at t equals to 4. T equals to 4, right? Now, t equals to 4, P3, and started at t equals to 4. It finished at t equals to 5 and did not appear again here, which means it has only one waiting time, which is 0, right? And the response time is 0 as well. Now, what about P4? P4 arrived at t equals to 5. 5, right? But it started the service at t equals to 7. So in this case, it had been waiting from 5 to 7, right? From the time it arrived to 7. Started the service at 7 means 2, right? The waiting time is 2. And how many times it had been waiting? Only one time, which means the response time is 0. 0? 2, right? Which is equivalent to the very first chunk of waiting time, 2. Now, if you sum these, divide by 4, you'll find that the average waiting time is 2. However, you can calculate also the response times, right? The response times, we said for this one is 0 for P1. For P2 also is 0 because it arrived at 2 and started at 2. For P3, it arrived at 4 and started at 4, so again 0, right? However, for P4, it arrived at 5 and started at 7, so it's 2, right? So 0 plus 0 plus 0 plus 2 divided by 4, half, okay? Half milliseconds, that's the response time, average response times. P2 before P4. Why we get P2 to get the service before P4? Well, when the time was 2, no, we look at the timing here, okay? Where you want here? Here? Okay. So at the time equals to 5, so we're talking about the time equals to 5 here. Why we let P2, not P4? At the time equals to 5, whom we have in the queue? We have 3 processes, okay? P2 that needs 2, P1 that needs 5, and the new arrival, which is P4, that needs 4. So which one of them needs the least? P2. That's why we serve P2 first, okay? Now, the other CPU scheduling algorithm is called round robin. Round robin is an easy one here, which is the basic round robin. Basically, in round robin, the idea is like this. Processes are served based on FIFO policy. FIFO. However, there is one additional constraint, which is a process cannot spend in the CPU more than a fixed amount of time that is known to be the quantum time. Quantum time. So if I say the quantum time is 10, means once a process is chosen to execute, it should not spend more than 10 milliseconds. The consequence is, if a process needs 10 or less milliseconds, it's fine with the process because it's going to finish anyway, right? However, if the process needed more than 10 milliseconds, then it is actually taking the quantum time, which is 10 milliseconds, and then it has to queue back with the remaining time. Queue back based on FIFO policy, right? And then the time is chosen again. It will be given another 10 milliseconds. If it's finished, it's good. If it's not finished, then it has to queue back again. Okay? So here, it's FIFO with one additional constraint. The maximum amount of time a process is allowed to execute is given by a constant fixed, which is basically called the quantum time. Okay? Now, if this constant is large enough, means all processes will finish once they're given the CPU, right? Because the quantum time, the time they are allowed to execute, is much more than what they need. So we will end up with what? FIFO, right? FIFO, first come, first serve, or first in, first out. And if the quantum time is small, too small, then what? Too many context switching. Too many context switching. By the time the process started to execute, very fast after that, we have a context switch. So the CPU most of the time doing what? Context switching. And context switching is expensive because it's overhead, right? So it should be something that is reasonable, okay? Reasonable. Anyway, the information that I mentioned before about the times for the quantum time is 10 to 100 milliseconds. To correct what I said before, the 10 to 100 millisecond is actually the quantum time usually, the choice of the quantum time, and the context switching is between 0.1 to 1, okay? And that will make the percentage, okay, of servicing a process and the context switching to be what? 1%, okay? Which is 0.01, 1%, right? Let's trace this round robin with the simple example to see how does it work. Assume that you have the following processes. Of course, we can make this a little bit more difficult when we add the arrival times. Okay, arrival times. So if a process is the only process in the system, it needs 100 milliseconds. While the quantum time is 10, then basically after finishing the very first quantum time, it will continue the next one, isn't it? Because it's the only process, okay? So that's what you will need to consider when we have arrival time. And now if we have processes P1 to P4, and these are the burst times that we assume that they will take, okay? But our scheduling policy does not use this, right? Does not affect the schedule. So these burst times that I've been showing, they do not affect the scheduling policy. The scheduling policy don't look at them at all, right? Only when we talk about shortest job first and shortest remaining time first, we look at them. We need that information for the scheduling policy. So here, P1, so all of these processes, they are there in the system at t equals to 0. And they are in this order in the queue. This is the front of the queue, and this is the rear. So serving from the front. Now, P1 will be served, and the quantum time is 20. But however, it needs 53. So we're going to give 20. And it's left with 33, right? So you're going to write here P1, 33. And then queue at the end of the queue, right? So P1 will be moving where? After getting service for 20 milliseconds, will be moved to the end of the queue with 33 milliseconds left, okay? And then I serve P2, that needs 17 milliseconds. And the maximum that can take what? 20. Okay, it finished after 17 milliseconds. What am I going to do with the remaining 3 milliseconds? Of course, take another process, right? The CPU is supposed to take another process. So it will finish at t equals to 37 there. And at that point, we'll take the other process, which is basically P3. That needs 68. 68, but it can only take 20. So at t equals to 57, the process P3 has to queue where? Here, at the end of the queue. And it will be queuing with what? 48, right? 48. So it will be queuing behind whom? P1. Okay, P1 is left with 33. And then after that, we have the P3 left with 48, okay, at the end of the queue now, right? At the end of the queue here. And then you take P4, that needs 24 milliseconds. 24 milliseconds means it will be given 20 milliseconds first, from 57 to 77, and it will be queuing for the remaining 4 milliseconds. It will be queuing behind P1 and P3. P1 and P3. Now, it's P1 turn again. So P1 now becomes what? The head of the queue, and it's left with 33 milliseconds. However, we can give only 20. So at t equals to 97, it has to leave, okay? And it will be queuing at the end of the queue with 13 milliseconds left, right? Now P3 will take over at this point, and P3 is left with 48 milliseconds. We'll be given only what? 20. Okay, and it will be queuing for the remaining. And then after that, P4 that was left with 4 milliseconds now can finish from 117 to 121. Then we'll take over what? P1, the CPU, will take over P1. And that will finish, okay, because it only needed 13, right? And then P3 can be executed until it's finished, okay? So it'll be given the remaining, that is 20 and 18, okay? So this is round robin, okay? Processes, they get faster response, okay? And there is a bound, an upper bound, okay, to this response if we know the number of processes okay, queuing in front of a particular process. So a process arrived at the queue and found that there are 5 processes in front of that process. It means on maximum, this newly arrived process will be waiting for 100 milliseconds because the quantum time is 20. And the ones queuing are what? 5. Plus the time of the process that's already in the CPU, the leftover time for it. Okay? So this is the comment about the quantum time. We have been mentioning that the quantum time, if it's too long, okay, we will not have context switching. Once the process started, it will be finished. Okay? And so we end up with FIFO. So it's not something new, round robin. But if we have context switching every 1 millisecond, then for a process that needs what? 10 milliseconds, how many context switch we have? 9. Okay? 9 context switching. And if we have the quantum time to be 6 or 5, okay, then basically we have what? 1 context switch. Okay? So if you have to choose only one of these 3, which one you will be choosing? The middle one, right? So you will not be choosing the last case because many context switch, and we know that this affects the performance because it's delays. And we will not choose the first one because basically this is a FIFO, right? It is a FIFO, not round or robin. Next, we talk about priority scheduling. Okay, preemptive and non-preemptive. In the meanwhile, you have some class sheets there. Okay, basically examples that you can follow. Okay, please follow these at home so that you already practice it. You know how does it traced.